All right, so this week there was a problem-solving request to go over finding absolute extrema and checking on the boundary. So I picked this example because the example from the lecture videos was over a circle, so I figured doing a rectangle would be nice. And so our approach for this type problem is that first we just look for the extrema that we get from looking at critical points of the function we're given. So that means that first we start by trying to find grad f equal to 0, where my grad f I get by first filling in the partial derivatives with respect to x, so that's going to give me 18x, and my partial derivatives with respect to y, which are going to get me minus 8y. And if I want that to be equal to 0, it's the vector 0. I do it component-wise, and so that's going to give me the system of equations where the first component of my vector is equal to 0 and the second component of my vector is equal to 0. So this function doesn't have a whole lot of points. The only one I can possibly find is when x is 0 and when y is 0. So the one point I need to check is the point 0, 0. So I could go ahead and check that one right now. So f evaluated at 0, 0 is just 9 times 0, minus 4 times 0 is just 0. And so that tells me inside this area, there's my y, I need both directions, and here's my x. So up to y equal 2, down to y equal minus 3, up to x equals 2, down to x equals minus 2. Around that region, I only found one point that satisfies the gradient equal to 0. That's at the origin, and I know at that point my function is equal to 0. So I'm just wondering where else could I possibly have a maximum or a minimum? And it's not possible at this point for me to have any more maxima or minima inside the rectangle. So I'm kind of like, okay there. I just need to ask myself if around the edge of the rectangle, I'll try highlighting that. That needs to be much smaller. So now I'm just wondering if along these edges here, do I have maxima or minima there? The reason being that I'm thinking about this function being something that happens in 3 space. So z, or my f, is up there. Here's my x, here's my y. I've got this rectangle that I care to think about. And then my function is kind of a sheet shape. It's going up in x, but kind of going down in y. It's kind of like a saddle. And so at the origin I'm at 0, but as I move towards those edges my function could be increasing or decreasing. It's not a local maximum or minimum except for that I cut off at that point, and so it could be the highest or lowest point I managed to go through before I stop thinking about the function. This is a lot easier to take in if you try like looking at GeoGebra or something. I'm not so good at drawing 3D graphs. But anyhow, the important thing is that now I'm just wondering about my function I think I had written those bounds. Now I'm just wondering what values does my function take on those bounds. So I'm just going to think about my x equals minus 2. Um, 9 times 4 is 36. minus 4y squared, or my x equals 2 is going to give me the same thing because of the squareds. So I'll still have 9 times 4. Just instead of minus 2 squared giving me 4, it's plus 2 squared. Oops. And then y equals 2. So here I'm just plugging in my y squared is 2 squared. It doesn't match the 9 before because this rectangle is off-centered for whatever reason. So that's going to give me 9x squared minus 16. And the thing that I'm asking myself now is, along these edges, what's the highest possible value I could reach and what's the lowest possible value? Where for these, my x equals minus 2 and plus 2, I still have to only be allowed to plug in y that takes on those values. And for my y equals minus 3, y equals 2, I still can only plug in these values for x. So kind of what I've done here is, for example, my first line where I plugged in x equals minus 2, I've said what the value of f is going to be along this line. And the only freedom I have now is to pick the y value along that line to try and make my function as big or small as possible. So the biggest number I could possibly have, I have 36 minus a positive number because y squared is always going to be positive. So if I want to make this as big as possible, I'm just going to plug in 0 for y so that I don't subtract anything. That would give me 36. That's the biggest my number can possibly be. My minimum is going to come from trying to make this as small as possible. So it's 36 minus some number. And so if that part is as big as I can possibly make it, then my minimum is kind of reached. So the biggest number that I'm allowed to plug in is minus 3, because minus 3 squared is 9. But that would just give me 36 minus 4 times 9. 4 times 9 is 36, so that's actually just going to give me 0. I don't know why I did that, sorry. Maybe if I change pages it'll go away. There we go. 36 minus 36 is 0. So that is the minimum along these lines, but this 0, like I already had that function value, so this isn't going to do a lot for me. So that's going to occur for like 2 minus 3 or minus 2 minus 3. The x values don't really change anything here. And then the maximum occurred for 2, 0 or minus 2, 0. For the two cases down here, they're actually different because of that offset rectangle, so we are going to kind of have to think about all of them. So I'm just going to label them maybe A and B and do it below here. So for A, if I want to make this as big as possible, that means that I want to plug in the biggest number here that I possibly can, because no matter what, I'm subtracting 36. So the biggest it can be is when I try to discount that 36. Unfortunately, we're going to run into the same issue that the biggest I can possibly make this is 36. So suppose I plug in 9 times 2 squared or 9 times minus 2 squared. I'm just going to get 36 minus 36. Again, that 9 times 4 is 0. So the minimum I can get along this line is going to happen at plus or minus 2 minus 3, and it's going to give me 0. If I want to make this value as small as possible, I just want to have as little to subtract from as I possibly can. I want this positive part to be as small as possible, that way the minus 36 can do as much as possible. That's going to happen when I plug in x equals 0, take away the positive part entirely. 9 times 0 minus 36 is just going to give me minus 36. And so this minimum is happening at 0, comma, minus 3. And we can do the same thing for part B. So again, I want to take the biggest value x I'm allowed to plug in order to try and get the biggest possible value when I subtract 16. So that's going to be 9 times 2 squared minus 16. So that's going to be our 36 minus 16, which is just going to be 20. 9 times 4 is 36, minus 16 is 20. Yeah, so the maximum value that we can take on along this line is going to happen at plus or minus 2 for y value 2, and that value is 20. This is the largest value I can take on along this line, but it's not bigger than the other biggest value I've found so far, so we're not going to actually end up using this. And then to find the minimum, again, I'm just going to plug in x equals 0 because that's my way to make this part go away and preserve the negative that makes things small as much as I possibly can. So 9 times 0 minus 16 is going to be 0 minus 16, or just negative 16, and that's going to happen when I'm at 0, comma 2. And then recall we had at 0, 0, the function value was 0. So if I'm looking for the very largest my function can be and the very smallest my function can be, sorry, my dog has a bone in the background. Here's the smallest number, the minimum. Very large negative number is small. And it happened for x equals 0, y equals minus 3. And then the very biggest my function could be was my positive 36 over here. And that happened when I plugged in x equals plus or minus 2 and y equal to 0. So if I wanted to report my findings, I would say that my absolute minimum is minus 36 at 0, comma 3, I think it was. 0, comma minus 3, that's my bad. And then my absolute maximum is going to be positive 36 at 2, 0, or minus 2, 0. Yes. And that's how you answer this type of problem. So just to go over the steps, we begin with just setting the gradient equal to 0 to find points inside the region where we're kind of changing direction because that tells us that we might be at a maximum or a minimum. Once we find those points, we can just go ahead and plug them into our function and see what value we get. In this case, we got 0, and so we just kind of remembered that and moved on. And then we consider where our boundary is. That's this picture right here. And maybe you can already see the idea that the maximum is going to happen at the edges of x based on how I drew this. It's an upward facing parabola in x. So when I hit my boundaries, I'm at the part where that parabola is going up as much as possible. And it's a downward facing parabola in y. So that part of the drawing is maybe less clear, but that's why as we extend along y for x equals 0, we're going to find a minimum. And that's exactly what we found. When we looked at the edges of x, we found that plugging in y equals 0 and looking at the very furthest values x got us the maximum. And then we tried on the edges of y, and then we were able to see that when we plugged in x equals 0, we found the minimum. And maybe when you look at the function f, you could see that the most positive you can be is take the biggest value x and least important value y. And then the smallest you could be is take the least important value x and the biggest possible value y. I gotta click on here. And all this plugging it in is just to kind of convince ourselves of that fact. And then we identify the largest and smallest values and report those as absolute maximum and absolute minimum. Kind of just one last note, the example that I did for you all in the videos, the boundary was given as a function. That made it a little bit like easier because there was just one thing to plug in. When you can solve for y in terms of x for your boundary, you can go ahead and plug that into f and then just consider changes in the other variable. For this one, they weren't really related to each other. They were just these straight lines, and so that's why I plugged in the numbers one at a time this way. But you would want to rely on the other approach if you were given a shape in the xy plane where x and y are related. So that's all I've got for today. Thank you for requesting this video, and I'm going to get it uploaded as soon as possible.